All right, Algebra 2 people. As we move along, we are now going to start exploring horizontal asymptotes. Okay, we've already talked about vertical asymptotes. Those are weird things where the x gets interrupted, but today we're going to talk about horizontal. They're a little bit different. They're mainly concerned with what happens to the far left and the far right. What happens as x approaches infinity? Okay, both on the positive side and as x approaches infinity on the negative side. What does the graph do? Okay, so what does it do when the x values get extremely big or extremely small as you go negative? To larger and larger magnitudes, but they're negative. Okay. So one of the things, another way of thinking about this is the height of the line. What happens as it goes off to the right, really, really far distant? How tall is it? Does it seem to reach a consistent height? So you can see the vertical asymptotes in here. Okay, we're not going, and we could tear apart that denominator and figure them out, but we're going to play with the horizontals today. Okay, so as this thing goes really, really far to the left, it looks like it is reaching a height of 0. Okay, or well, it approaches that. And as it goes further and further left to negative infinity, it's going to get closer and closer and closer to 0, but as it's heading for infinity, it's never going to actually touch it. It's just going to get close to it. Okay? Same thing on the right side. It's going to get closer and closer and closer and closer, and it looks like it's also bottoming out at ground level, which is a height of 0. Okay? Another way of thinking about this is you're looking for the end behavior of the graphs, the left end and the right end. So the right end is the part that approaches positive infinity, and the left end heads for negative infinity. Okay, so this is the equation above it that made this graph, and it looks like it's headed for 0 on both sides. Okay, so it's not a super symmetrical graph, but it is doing the same thing on the left side and the right side. Now this one we've kind of cheated. There's a dotted horizontal line that is the asymptote. Okay, the dotted line isn't part of the function line. It's telling you what this is approaching. Okay, so as it gets further and further out and closer to both ends of infinity, it's approaching a height or a value, okay, of 2. Now, horizontal asymptotes are weird because if you're not looking at infinity, they can cross their horizontal asymptote. Okay, but we don't really care what happens in the middle. We're caring about infinity. And as they get out to infinity, they do not cross it. Okay, they're actually nowhere, they're approaching it, but they cannot cross it. Okay. So the y value, or the height, as they get out on both sides, even though these graphs really aren't that symmetrical, they're doing the same thing on both sides. They're both approaching a y value, a height of 2. Okay, here's the other thing they can do. So they can bottom out on the x-axis, they can bottom out at 0, they can approach a height of a number, or they can do this. And this just seems to be getting bigger and bigger and bigger and bigger. And on the other side, it appears to be getting smaller and smaller and smaller and smaller. It doesn't seem to be approaching any set number. So are they doing the same thing at all? Well, and that's the really strange thing about this is if you run a line near them, they actually are, both sides of it, approaching the same straight line. It's just not horizontal. Okay, so this is not a horizontal asymptote because it's not horizontal. Okay, for horizontal, you have to be going ground level, left and right. Okay, y equals 2. y equals 0. Okay, those are horizontal, single numbers. This is a linear function. This is a line, like a y equals x line, or, well, in this case, a y equals 2 line, y equals x plus 2 line. We'll figure out how to find that line next time. But in the meantime, just realize it's not a horizontal asymptote. It's actually something called a slant asymptote or an oblique asymptote. It goes by both names, so you'll hear it referred to both ways. And the word oblique, you may remember that coming out of geometry. If you have a prism, okay, if it's like perfectly box-like, it's a right prism, okay, but if it's slanted on its side, that's an oblique prism. You have a right prism where the height is also an edge, and if it's slanted, that's an oblique prism. So oblique prisms exist on a slant. So that's kind of where the name comes from. Okay, but how can we tell, just looking at the function, what it's going to do at the end? How can we find the end behavior? Okay, what are we going to do? And it comes down to comparing degrees. It comes down to the degrees. Okay. What we're looking for when we talk about degrees, remember how we name polynomials. If you name them by degrees, okay, you're looking at exponents, because that's where the little circle degree symbol goes. It goes up in the exponent spot. So what we're looking for are the big exponents, okay? So here's the function with its graph. Here's the function without its graph. And let's see if we can figure out mathematically what happens when x approaches infinity. So first of all, find the highest degree, and it's right there. X squared, that's the biggest degree in the rational. Okay, what happens when this thing approaches infinity? Well, it's squared. That's infinity squared. What that means is the rest of the function is going to stop mattering. It's like if you had a billionaire and you walked up to the billionaire and you said, "Hey, have $3." He's still a billionaire. You wouldn't call him a billionaire plus $3. Okay, and he might be grateful for it. He might not, but as far as just making a dent in his life savings, it doesn't. Okay, he's still just a billionaire. Anyway, the rest of it, when you're approaching infinity, we're just going to call it meh. So x squared matters, okay, but the rest of it doesn't matter, okay, because you're approaching infinity. And as you plug in bigger and bigger and bigger values of x, the rest of the function is going to kind of basically take a back seat, and x squared is going to take over because he's going to be so big, he's going to overshadow everybody else. Now, there will be an infinity back here. You have -3 times infinity, but the front, the highest degree, that's infinity times itself. Okay, yeah, you got 3 infinities behind it, but infinity times infinity stacked on infinity? Meh, we don't care. So what ends up happening is you get this massive x squared with infinity squaring on itself. And so the question is, well, what happens when you get such a big number in the bottom of the equation? What does it do? So let's look at what fractions do as the denominator gets bigger. So 1/1 is just 1, but we're going to make a bigger denominator. 1/2 is 0.5. And we're going to keep the math simple. Let's go 1/10. That's 0.1, okay? And again, we're just making a bigger and bigger denominator because we're going to approach infinity. 1/100 is 0.01. Now look at what's happening. 1, 0.5, 0.1, 0.01. Okay, as the denominator gets bigger, the numbers get smaller. The answers get smaller. 1 divided by massively big numbers as x approaches infinity. Okay, the top, it really doesn't matter what's on top. Any top divided by massively big numbers is going to head for 0. It's going to get smaller and smaller and smaller, and it's going to get so close to 0, it will never actually touch because you can't actually divide yourself to 0, but you're going to get really, really, really small, really tiny, really close. And it's going to happen on both sides. Okay? So, the moral of the story, if your highest degree is on the bottom and everything else is meh, okay, so there can be stuff with your highest degree, there can be stuff on top, that part doesn't matter. If your highest degree is on the bottom, you have a horizontal asymptote at 0. Okay? And again, this only applies when x approaches infinity. Okay, so this applies on the far left, the far right. The middle, we don't really care about. Okay, so as you approach the far left, you're going to head for infinity. As you approach the far right, you're going to head for infinity. Both sides, you're going to hit a height of 0. Okay, so let's try it again. We're going to be looking for our highest degree. Okay, and there's a tie. There's 2 highest degrees. Okay, if there's something in front of your highest degree, it gets included. Okay? Adding, subtracting numbers, no. But multiplying numbers like that 2 times the x squared, that does matter because you've got infinity squared and then you double it. So the question is, okay, well, what happens now if we're tied? Okay, remember, this only applies when x is approaching infinity. Okay, and this is a trick to find horizontal asymptotes. Okay, we've got the meh stuff, but then we've got x squared, and it kind of cancels. This is a fake cancel. Okay, this is not a real cancel because these are both, well, the bottom one is part of a polynomial. So you can only do this when you're checking for horizontal asymptotes. Okay, the meh doesn't matter. The x squareds just cancel, and it leaves you with 2 over, and there was a 1 in front of that x squared. Okay, that means your height, as you approach infinity with the x, is going to be 2, or 2 over 1. And if we look back at the graph, that was it. Okay, it took them a while. They weren't getting there really quickly. At least, we had 10, negative 10 on both sides of the graph. But eventually, as we get further and further away from the origin, it is going to level off at a height of 2. And again, it doesn't matter what it's doing in the middle. Yeah, it crosses the horizontal asymptote in the middle. Horizontal asymptotes only take effect when we're headed for infinity. So again, pay attention to the high degree. If your high degree is on the bottom, you head for 0. Okay, that's like saying 1 over something really big. Okay, but if you're tied with your high degree, okay, you have an x squared on top and bottom, and that's the highest, or an x cubed, an x to the 4th, or even just an x. Okay, if your highest degree is tied, what you do is you take whatever was in front of the highest degree, both top and bottom. Okay, whatever was in front, that's the height as you approach infinity. Infinity basically wipes itself off, and you're left with whatever was in front of your highest degrees. Okay, so there's a third thing that can happen with your highest degree. It could be on the bottom, it can be tied. Here's the third thing that can happen. It could be on top. All right, so we found highest degrees all over the place. We found them on the bottom, we found ties, and now we find one on top. What that means, your x squared is over meh. The rest of it really doesn't matter as you head for infinity. Okay? You've got something on top that's just big, and it's going to get big and 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 big, and nothing's going to stop it. Okay? The bottom is worthless. Nothing's going to stop it. Okay? It's just going to get big forever. It's going to slant up. There is no horizontal asymptote. Okay? There is nothing to put on the brakes. The thing that's stopping everybody else is you've got high degrees in the bottom. Okay? Nothing stops this. There is nothing in the bottom to put on the brakes. Okay? Your landing gear is useless. You're just going to go up forever. You've got a rocket. Okay? So, if your high degree is on top, and you've got meh, and you can also have meh up with the high degree, but if your high degree is on top, okay, it's slanted. If it's a negative high degree, by the way, it slants the other way, so you can get a slant going down. But again, it's still, the high degree is on top. There is no horizontal asymptote. Okay, so these are all the possibilities. High degree on the bottom, okay, in the denominator. Another way you can think of this is if it bottoms out. Okay, it's too heavy on the bottom. Your landing gear won't go up into the plane. You've got weights on. You're tethered. You're going to hit zero eventually. If your high degree is tied, it's whatever was left in front. If your highest degree is on the top, that's like having something giant over 1, and it really doesn't matter what's on the bottom. You might as well just call it 1. It could be called anything. It's meh. It's just going to get big forever and ever and ever and ever and ever and ever and go up forever and ever and ever. Okay? Never stop. There's nothing on the bottom holding it down. The bottom's the anchor. Okay? If there's nothing on the bottom that can stop it, it will get big forever, and there is no horizontal asymptote on that. Okay, so let's actually try this out, because there's a lot of theory in what happens on the top, what happens on the bottom. It's actually pretty simple once you start doing it, once you start using it. Okay, so in these example problems, we are going to look for the biggest degree and determine what's going on with our end behavior, what's going on with the horizontal asymptote. So biggest degree is on top. It means the rest of it doesn't matter. So you have a big thing over whatever and nobody cares. Okay, big on top, big, big, big. It just builds on itself. Build, build, build. It goes up like that. That's not horizontal. Okay, that is a slant. There is no horizontal asymptote. Okay, so if your highest degree is on top, you just get big forever. If you're big on top, you're big forever, and you slant upward. Okay, we are looking for more high degrees, and I've found that they are tying. Okay, the negative gets included because he's attached to the front of the big degree. So we have negative big over big, because when you plug in infinity, they're going to get big. And the bigs kind of cancel out. Not exactly, and that's why you don't actually touch the horizontal asymptote, because, there's still a negative 4x, a plus 2x, and a negative 3 in there, but it's close. It's close enough to estimate. Okay, in front of the bigs were hidden 1s, negative 1 over 1. That's it. We just found the horizontal asymptote. So if they're tied, you just look at what's in front of them. Okay, so x squared over x squared cancels, and whatever's left, that's the horizontal asymptote. You can also think of that as the height asymptote. It's how tall it is, what value it levels out on, so the height or the y value. Okay, we're looking for highest degrees, and found them again. Okay, this is where the highest degree is a hidden 1. It's not really all that high, but it's the best we've got. Okay, so we've got big over, and the plus 3, again, doesn't matter. The 4 does, though. If it's in front of that thing, okay, and it's a multiplier, not an adder, not a subtractor, a multiplier, okay, that's 4 times the big, okay? Those big things are going to cancel, and you're left with, now the 4 is on the bottom. It has to stay on the bottom, okay? But on the top, that's just 1. It's a hidden 1, but not so hidden anymore. Okay, and that 1/4, that is the height of our end behavior. The graph is going to level out at a height of 0.25. Okay, that's your horizontal asymptote. All right, last example. We're looking for the biggest degree, happens to be on the bottom, with a negative 3. The negative 3 would matter if there was something on top to cancel it, but the problem is there's a 7 on top. The 7 doesn't matter when the x gets big, and as a result, the -3 really doesn't matter either, because the big is in charge, and he's going to get big, 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 and it's like an anchor. Okay, so he's going to get huge. So 1 over huge. Okay, that's a giant anchor that's dragging your function down, and it's going to hit the ground. Okay, and ground, that height is 0. Okay, so 1 over a huge number is going to get awfully close to 0. So it's headed towards 0, even though it'll never quite get there exactly. It's going to give it its best shot. And that's all you have to do to find horizontal asymptotes. Now what if on our worksheet we didn't just have to find the horizontal asymptote? I mean, that'd be nice if that's all we had to do. But what if our worksheet also wanted us to find the vertical asymptote or the holes, the discontinuities? What if we had to do both? Okay, in this instance, we've already gone through and found the horizontal asymptotes. Okay, and you find them just by looking at degrees. Okay, where they tie, where they bottom out and the anchor causes us to hit the ground at 0, where they're on top and they just slant off forever into oblivion. Look for the horizontal asymptotes first. Do these guys first, because you don't have to tear the fraction apart to find them. You can find them just by glancing at it. Okay, the vertical asymptotes and the holes, those are the ones where we have to factor, we have to cancel. Okay, that's that group. Okay, that's what we did last time. The horizontal asymptote, you don't need to take anybody apart to find. Okay, but the vertical asymptote and the holes, where we factor, we're looking for the greatest common factor, or we're taking them off into parentheses because there's an x squared that didn't disappear with a greatest common factor. Did they cancel? That's where you kind of have to tear the fraction apart to find them. Okay, so let's begin. First of all, we already have the horizontal asymptote. Okay, that means we can start tearing the fraction apart. We don't need the whole fraction intact anymore. Okay, so the vertical asymptote and holes are kind of the last thing you do in this. Okay, and you're looking in the denominator. Okay, they come exclusively from the variables in the denominator. Okay, so first of all, this variable has a greatest common factor attached to it. We're going to take out the 4, and that leaves behind x minus 1. Okay, we know something weird. There's a discontinuity at 1. Okay, we don't know if it's a hole. We don't know if it's a vertical asymptote. We don't know what's going on. We just know it's there. Holes can cancel. VAs cannot. Okay, so we're going to kind of rip the top apart and factor it to see if anybody can cancel the x minus 1. Okay, 3 and 1 times to 3, they also subtract to 2. So those look like good factors. The catch is they need to subtract to a -2. Okay, so 3 times 1 needs to be a -3, but the combination of combined like terms, that has to be a -2. So the 3 goes negative and the 1 goes positive. And x plus 1 doesn't cancel x minus 1. They cannot cancel. They're conjugates. Conjugates don't cancel up and down in fractions. So x minus 1 cannot be removed. It is a vertical asymptote. Holes can be removed. Vertical asymptotes cannot be removed. Okay, so we have no horizontal asymptote. And we have a vertical asymptote at the 1 on the x. Okay, this guy, we already know there's a horizontal at -1. We're going to tear apart the bottom now. And this is actually really similar to the last problem. 3 times 1, still subtract 2 and times 3. Only this time, we're subtracting to a +2. We'll fill in the 3 and the 1. If we're going to subtract and get a +2, it's probably +3 minus 1. So 3 minus 1, that's +2. 3 times -1 is -3, so the factoring works. On the top, there are a couple of greatest common factors here. And guys, if your highest degree, either top or bottom, has a negative in front of it, pull the negative. It just makes life easier. Okay, so we have pulled the negative. Because we pulled the negative, it affects the sign of everything left in the parentheses. Okay, now remember, it's the denominator, okay? The denominator that makes these discontinuities. Don't pay attention to the numerator. The numerator is just there to tell us if something cancels. Just the denominator x's are what we're caring about, okay? So the first group is going to create a -3. The second group is going to create a +1. Those are the places where the graph hiccups. Okay, the question is, how does it hiccup? Does it make a hole or does it make a vertical asymptote? Okay, nothing is canceling. If nothing cancels, it is a vertical asymptote. So giant canyon in the graph at -3 and 1. Okay, this guy. We've got a greatest common factor in the bottom. You can pull out a 4. It's common to both of them. And that will leave behind an x minus 2. The top is a group, okay? So don't forget there are groups running around through all of these, okay? Those groups don't cancel. Nothing is going to cancel. So that means that, and remember that the 4, you can't say, oh, if I plug in a 0, it will kill the 4. There's no x out there. So this only applies where there are x's. That's why it's really critical to pull x's where you need to pull x's. So the graph is hiccuping at a value of 2, and it's not canceling. That means it's not removable. So it's a full vertical asymptote. Last one. Here we go. Okay, 7 on top is about as simple as it gets, but this has a common factor of 3. We don't have to slide divide. We can actually pull the 3 out. And because there's a negative in front of our lead term, pull the negative. It will mean you can go straight into factoring and you won't need slide divide. Now, if we're dividing by a -3, it's going to alter the sign. So we're going to get a -2x and another -3 in the back. Okay, and if you need to redistribute to see if you got it right, feel free to do that. Now, we've actually had this one before. X squared minus 2x minus 3. We already know what that factors into. That hasn't changed. So still with a 7 on top, -3 out front, and then we should get an x minus 3 and an x plus 1. And none of these guys are canceling again. Okay? Nobody's canceling. And you can always check to see if the factoring works, etc. Okay, again, look for where the x's on the bottom are. Okay, one of them's making a 3, the other one's going to make a -1. Did anyone cancel? Well, this one's kind of, again, they're all kind of boring, actually. There's no holes at all. Everybody has giant canyons. Nothing can be removed, so all vertical asymptotes. And that's how you do the horizontal and the vertical at the same time.